We are literally surrounded by it every single day. It's this invisible force that powers our whole world, and it's hiding right there, in plain sight, inside every single wall. But here's the thing, behind all that convenience, there's a danger we tend to forget about. So today, we're going to pull back the curtain on the electricity we all use and talk about why it demands our absolute respect.
Okay, so let's just dive right in. Why is the current coming from a simple wall outlet so dangerous? I mean, think about it. We plug stuff in all the time without even a second thought. But what is actually going on inside those wires?
Well, the answer really starts with this number right here, 75 milliamps. And that's just 75 times 1,000ths of an amp. It's such a tiny, tiny amount of current, it's almost hard to believe. But if that little bit of current passes through your chest for just 5 seconds, it can trigger something called ventricular fibrillation. That's where your heart just starts chaotically quivering, and yeah, it's often fatal.
And that brings us to this absolutely critical quote from a high-voltage safety manual. It says the frequency used in our power grid, 60 Hz, is literally the worst possible frequency for the human body. The worst. So you have to ask, why? What is it about this specific rhythm that makes it so uniquely dangerous? Well, to figure that out, we've got to understand the rhythm itself. All right, so to really get why 60 Hz is such a problem, we need to understand its rhythm first. Let's kind of unpack the basic flow of the electricity that's powering pretty much everything around us. Okay, so you've probably heard that electricity comes in two main flavors, right? AC and DC. Now, DC, or direct current, that's the simple one. It just flows in one direction, kind of like a river. A battery is a perfect example of DC. But AC, alternating current, that's what's in our walls. Its flow is constantly changing direction, back and forth, more like an ocean tide.
And here's the cool part. This back and forth flow isn't chaotic at all. It actually follows this perfect, totally predictable pattern called a sine wave. It's just the smooth, rhythmic wave, right? It rises up to a peak, falls back through zero, hits a low point, and then comes back to zero again, over and over, in a continuous cycle.
And that brings us to the whole idea of frequency. Frequency, which we measure in hertz, is just how many of those complete sine wave cycles happen every single second. So when we say our power grid is 60 hertz, what we're really saying is that the current is completing 60 of those full cycles, flipping its direction back and forth every single second. Whoa. Okay, but think about this for a second. How do you even measure the power of something that's constantly changing like that? I mean, it's hitting peaks and valleys 60 times a second. You can't really use the peak value because for a split second in each cycle, the power is actually zero. So we need a better, more practical way to measure its true effective power.
And that is where something called the RMS, or root mean square value, comes into play. Just think of it as the effective value. It's basically a way of saying, what's the AC voltage that gives you the same amount of oomph, the same heating effect as a DC voltage? It's the practical measurement. So when you hear that an outlet has 120 volts, you're actually hearing its RMS value.
And look, here's where we see why understanding RMS is so incredibly important for safety. The manual doesn't just say more than 30 volts is dangerous. It specifically says more than 30 volts RMS. That's the measurement that really matters. It's what establishes that clear, undeniable threshold for danger.
Okay, so we've got all the pieces of the puzzle now, right? We have an alternating current, we have that 60 Hz frequency, and we know its effective power is measured in RMS. So now, let's connect the physics to our own bodies and see exactly why that 60 Hz number can be so lethal.
You know, the whole journey of an electric shock, it starts really, really small. At just 1 milliamp of 60 Hz AC, a person will just feel a slight sensation. You know, like a faint tingle. You can feel it, for sure, but it's not painful. But here's where the danger just skyrockets. At only 16 milliamps, we cross what's called the let-go threshold. That 60 Hz frequency causes a sustained muscle contraction. Your own muscles clamp your hand onto whatever you're touching, and you can't let go. You are physically trapped by the current itself. And that brings us right back to that fatal number we started with, 75 milliamps. At this level, that 60 cycle per second rhythm of the current starts to interfere with your heart's own super delicate electrical signals. It just completely disrupts its natural pace and sends it into that deadly fibrillation. It is the frequency that makes it all so tragically effective.
I mean, just look at this table. It lays it all out so clearly. Look at how fast it gets serious. At 9 milliamps, the shock is painful.
At 16, like we said, your own muscles betray you. By 30, it can paralyze the muscles you need to breathe. And at 75 milliamps for more than 5 seconds, it is probably fatal. The line between a tiny tingle and a lethal shock is just terrifyingly thin.
Okay, so knowing the danger is obviously the first step. But the next, and honestly the most important part, is turning that knowledge into action. So let's talk about the absolute essential safety procedures for anyone who works around high-voltage systems.
The safety manual breaks it down into this really critical 4-step process. First, and this is a no-brainer, always de-energize the equipment. Step 2, and this one is vital, you have to discharge any stored energy. See, things like capacitors can hold a lethal charge long after the power is off. Third is that classic rule you've probably heard, keep one hand in your pocket. Why? It helps prevent a current from passing right across your chest and your heart. And finally, of course, always use properly insulated tools rated for the job.
But you know, beyond just the physical steps, safety is really a mindset. Don't work alone. Take off any jewelry that can conduct current, and know the emergency plan before you even start working. But maybe the most important rule of all is this: never, ever, ever assume a circuit is dead. You have to check it for yourself, and then you check it again.
And here's a really key piece of equipment for that process we just talked about, the grounding rod. See, even after you cut the main power, some parts, like capacitors, can still hold a really dangerous charge. This tool is what you use to safely discharge all that stored energy. It's what makes the equipment actually safe to handle. This is an absolutely non-negotiable step.
Really, it all just boils down to this. The electricity in our walls is an amazing, incredible tool, but it is completely unforgiving. It operates by physical laws that do not bend for anyone, so we have to learn them, we have to understand them, and most of all, we have to respect them.
So the next time you go to plug in your phone or you just flip a light switch, maybe you'll think about that incredible rhythmic power that you're commanding. Now that you know the science behind this invisible danger, I have to ask, will you ever look at a simple power outlet the same way again?